About entanglement, of the quantized electromagnetic field. And as we've discussed, that entanglement is something that depends very much on what degrees of freedom you're thinking about. So that entanglement comes in many different flavors, especially in the context of entanglement in the quantized field. So we could be talking about entanglement in the polarization degrees of freedom between, say, two photons. Okay, that's an example of what we often call particle entanglement. They're properties of the particles. And the particles have spin. So we can talk about spin entanglement, which is in the case of photons, that means the polarization of the photons. And we could write, for example, such an entangled state if we wrote it in second quantized language or notation. This saying, I have a state which is a superposition of either two photons created in the same mode with the same momentum or wave vector in the same polarization, or this same K, but different one. Now, actually, this should be, of course, this thing. So what I'm saying here is that this state corresponds to, I can write this and you will see this, which is why I'm writing the notation this way, because in the literature it's written both ways, in this kind of second quantized way and this kind of first quantized way, where I think about a particle. If you knew nothing about second quantization, you said you had an electron in a plane wave state with a certain spin, how would you write it? Well, you'd say that electron has, this momentum, and then it spin up, right? That's what you would write, the state of a single electron in first quantized language. So this is the two-particle state in first quantized language. Is that clear what I'm saying? Right. So in this case, both photons have the same momentum, but they are entangled in polarization. Okay? And similarly, this guy is written crazily, so let me fix that, sorry. I could have a momentum entangled state of two photons where I think about, so this state, this is written here in second quantized jargon, or my notation, or in first quantized notation, where both photons in this case have the same polarization, say they're both horizontally polarized, but their momentum is entangled. Okay? So that's, I'm being quite cavalier about whether I put the tensor product symbol in. Sometimes I put it together with the comma. I hope you can understand this, that the notation is somewhat fluid, and we can understand just the context of what I'm saying. Yeah?
So you said it, HVVH.
Good question. Thanks, Chi. That's HHVV. Right? They're both in H or they're both in V. That's the particular state. Yeah. Yes. Sorry about that. Yeah.
And what is the relation between K3 and K4 and K1 and K2 there?
Nothing. They're just any moment that I choose. They're different.
Shouldn't they be the same? K1, K2, K2, K1 maybe?
If they're the same, then it's not entangled.
Yeah, like K2, K1.
But that commutes. That's the same state, right? If K3, if these two are these two, that's
Yeah, right.
the same state. That that would be alpha plus beta would be not normalized. Those are commuting operators here.
Yeah, but K1 and K2 can be the same. I don't know if that was what you were asking.
Maybe that was the question. I'm not sure.
I'm not sure to answer that.
Okay.
All what I'm saying is that if I had written this as K2, K1, that's not an entangled state. Doesn't matter that I wrote this guy in that order. Okay?
Yeah.
Or if this, right? I mean, obviously that's not.
Yeah.
So you should be careful about the first one type of. We had this kind of discussion a little bit. Professor Chandler asked the question about identical particles and so forth. If I have a state that looks like this, that's just, even though where I have two different particles, there's some notion of symmetrization of this, but this is not an entangled state. Okay? Even if I could put them like this, it could be in two different, that's not an entangled state. They have to have two different terms. Okay. Or we could have mode entanglement, and in mode entanglement, hold on one moment, let me just finish this comparison. In mode entanglement, what we think about is our tensor product space are the modes, not the particles, or the degrees of freedom associated particles. And that's, as you said, if you put a single photon on a beam splitter, from the particle's perspective, that's a superposition of two momenta states. This doesn't seem entangled at all. But from the point of view of the modes, it is entangled. Yeah?
So here, two particles are entangled, but is it entangled with the field? No.
I don't know what you mean. The particles are excitations of the field.
Okay, but
Now, they're not, the momentum is not entangled with the polarization. So that's separable.
okay. But here, momentum is entangled.
The momentum entangled, but the momentum is not entangled with the polarization.
But is it the momentum of the particle we are considering
That's right.
separately from the polarization of the field? Or, both are, two are different, right? What I'm saying that, so here and the state looks like one of the Bell states.
It does, yep.
Right. So,
But it can also, this can also look like a Bell state if I chose two specific momenta. Right?
okay. But
Okay.
here, that is the entanglement is in between two modes in the field, right? In this case.
Well, they are two different modes, that's right. But what I'm saying is that I could have, they could just be in this, so the modes, as we see, are defined by polarization and momentum, right? That defines our mode of the field. Now, this particular kind of entanglement involves a situation where you have exactly two photons, but the momenta of those two photons are entangled. It's a more of a particle picture. I can have exactly the same state for two electrons, right? I can have two electrons where, say, they were both spin up, and they were emitted, correlated in this way. So thinking about them as modes is not a productive way of thinking about it. I think about them as particles. So I could second quantize that and write it in terms of modes because the state is the same state, but it's more productive to think about them as particles rather than modes. Alternatively, there is mode entanglement. Let's follow through on that a little bit more. So as we discussed, we can make these kinds of entangled states through the process of parametric down conversion, spontaneous parametric down conversion. So the process of spontaneous parametric down conversion we discussed as a situation where I have some strong pump field at some frequency with some wave vector. And inside a II crystal, we have a situation where this big mama photon spontaneously decays into two daughters. And those daughter photons are correlated, and they're quantum correlated, they are entangled. Okay? So we have a situation where we have, for example, we have boy, this is really kind of crappy. Can you see that? The so-called signal and idler photons that we discussed before. And this happens for a whole rainbow of situations as long as we have phase matching satisfied. And that phase matching is an expression of energy and momentum conservation in the problem. So we can have a situation where I have as long as these guys add up, I guess this is the signal, this is the idler. I'm going to give up on this chalk soon. And in addition, energy is conserved. And as we discussed, in order to satisfy that kind of phase matching criteria, what must be true is this, the crystal has to be birefringent, and that we must take advantage of the fact that the index of refraction, because K depends on frequency through this relation, that we can have different indices of refraction for different polarizations of light. And that actually is quite important in terms of the way in which momenta and polarization are entangled in this problem, how we take advantage of that, and look how the crystals are oriented in order to achieve this phase matching. So in particular, what we saw was that you can kind of see this phase matching. If I do this, a rotation around here, all those colors, all the yellow photons and red photons, is a whole cone of red and yellow photons that satisfy phase matching. So this, what happens is you end up with cones of light that come out in certain ways. Okay? Now, in particular, what we discussed was there's two kinds of phase matching, that ways to achieve this phase matching condition, so-called type 1 and type 2 phase matching. In type 1 phase matching, in a given crystal, signal and idler have the same polarization. So the entanglement that comes out of here is momentum entanglement. Okay? So all these have the same polarization. What's entangled here is the fact that when I look at this head on, if I look at this picture face on, then you know, I have these different tones that are being emitted on this, in this problem. Now let me go a little bit better. And we have the situation, for example, I don't have, I guess let me put a green one in there. So here's yellow. Here's green. Doesn't really matter. The point I wanted to make, and see if I can get this straight, is that there are many different photon pairs that satisfy this phase mapping condition. So I could have a photon with that momentum, that plane wave, let's think that's a red guy, and it is phase matched with this guy. Okay? Of course, there's a whole variety. I might have that guy, and it is phase matched with that guy. Yeah.
So just would the inner code, the yellow, compared to the pink, would be higher frequency?
That's right. It's a higher frequency of light. Yes. This is meant to be actually the colors that come out. Okay? It's pretty close to that. I mean, you know, every quantum optics book loves to put, you know, one of these photos on the cover with rings. Those are actually, I mean, they're false colors. They come out at the infrared, because typically these are, you know, some UV pump that when you have it is about infrared colors. But it can be close to visible, pretty close to visible. So the point is that there are different colors and different directions. And you might have the degenerate case be this one. Right? That's the green guy. That's when they're equal in color. I have to think about whether I got all the angles and whatever. But the point, you get the point, there is a degenerate color. It's probably not green. Okay? So because there is it's indistinguishable which of these pairs was emitted, I have a coherent superposition that of the sort I just wrote down, this state that comes out for type 1 phase matching, the 2 photon sector of that solution is, you know, the integral over d cubed k signal k Eigler satisfying the phase matching conditions creating some, let's call it O for ordinary polarization. It could be H or V, depends on what we want to call it, K signal, K Eigler. So O here is the ordinary direction in the direction of ordinary and extraordinary waves in birefringent crystals. Okay? And, you know, this kind of state is of the sort that we wrote down before, often where we have the same polarization but different momenta. And we have a sum over many, all the different possible pairs of signals and Eiglers. So not just 2 terms, it's the whole continuum of terms in that case. And this is often, you know, so I have, in this case, the, you know, ordinary polarization, OO polarization factors out. And this is often, as we describe, this kind of momentum entanglement is typically broken up into 2 pieces. one piece that has to do with the color, and one piece that has to do with the direction. Okay, so from the point of view of the color, I have something, if to the degree that I have perfect phase matching, I have this kind of correlation in frequency. And then in addition, I have something that has to do with the transverse directions, and there's something like, of course they have to be opposite, they're opposite, the transverse moment, they have to be opposite with this, all the phase matching. This is often called, you will see this in the literature, energy time entanglement, and this is often called transverse momentum entanglement, although often the word transverse is left off. This has something to do with the spatial mode for the real optics people in here. This has to do with, I know, the Gaussian mode, or a Hermite Gaussian mode, or a plane wave mode. So there's mode entanglement in the sense of the spatial mode of the single photons, and there's time energy entanglement. And as we said last time, this is related to the fact, this, if I looked at this in the time domain, this is saying that the two photons are created together in time with a time separation that's essentially zero. Yeah?
So in order to have the same polarization for the signal idler,
Yep.
is it not that they need to be S-polarized? I mean, otherwise, if it's P-polarized, it cannot have.
Well, I mean, S and P have to do with relative to the plane of the surface here.
Yes.
Everything they're both, so it's perfect. Everything, they're both S and P relative to the pump. Now, what happens inside the crystal is a question of what is the index of refraction. I mean, it's the same way that, you know, these is details of nonlinear optics that frankly I don't know and I don't really want to get into. But the point is, as we discussed at the beginning when we came out with this, that if I had, for example, or a signal, I put in a signal here that is polarized like this, or let's do it the other way around. Okay, this is like this, and this is like this. This is the extraordinary direction of the crystal, and this is the ordinary direction. What comes out here is a yellow idler, which is polarized like that, in the ordinary direction. I don't know if you call those S or P. I don't want to get into it. But the point here is that these two guys are polarized in the same direction, and they're perpendicular to the pump. But I'm not thinking about the pump. All right. So, right, so that's what we said we have. In this case, we have this time energy entanglement and the entanglement related to the spatial modes. And if we put, often in these, the early experiments, the way they were done, you put little pinholes here, picked off the particular transverse mode you wanted, and then all the entanglement that people were looking at was having to do with the time energy entanglement. In addition, we can have polarization entanglement if we use type 2 phase matching. So in type 2 phase matching, the two photons that are spontaneously emitted in parametric down conversion, one is ordinarily polarized and one is extraordinarily polarized. And so they're orthogonal. However, as we discussed, if you, the way, it depends on these direction of these crystals and such, what ends up happening is that I have two sets of cones that look like this, with these different colors. Oops. Excuse me. Write myself something. Right. Oh dear. It's going to be hard for me to draw this. Okay, so what I'm trying to draw is the following. We have two sets of these supposedly concentric circles. One of them are the H polarized, and the other are the V polarized. They can be ordinary and extraordinary. However, there are these two special directions. And in those two special directions, I can't tell from the momentum whether or not it was H or V polarized. And thus, and those two special directions, which we would call K1 and K2, the state of the system in that case is polarization entangled. Because I can't tell whether the photon that came from here was either H or V. So I have both cases. And this phase here depends on the details of the optics that I don't know. Okay? So this is an example of a polarization entangled state. Now, one thing you might ask, can I have both? Wouldn't that be nice? Can I have a state, for example, that is of this form? That's a state that is both entangled in its polarization degrees of freedom and in its momenta. Such a state has been the jar that's been developed. It's called a hyperentangled state. In fact, people like to break this up into this kind of two pieces. They would say it's got polarization entanglement, time energy entanglement, as well as spatial mode entanglement. Now, how could you make such a state? Well, it's the first way that that was considered is the following. Suppose I have two of these crystals. Okay? So what I'm going to do is I'm going to arrange it such that in one of the crystals, I emit, remember, if I have type 1 phase matching, all the photons have the same polarization. So everything that's coming out of here was of the form of the same polarization. So suppose now I do the following. I have two crystals, put them back to back. This crystal emits all H polarized photons if the pump is polarized like this. The second crystal emits photons in its own cone, and they're all V polarized photons if the pump is polarized like that. Okay. You can arrange two crystals that do that. You'd have to orient the optic axis in the right way so that the indices of refraction are just right. But now suppose you do the following thing. I'm going to put the pump polarization at 45 degrees. So now I have the pump is in a superposition of these two possibilities. And if the coherence length is such that I can't tell whether the spontaneous down conversion happened in this crystal or that, well, then I have a coherent superposition of these two possibilities. And so the state that comes out of that crystal would be the following. In other words, what we did is just had two different type 1 down conversion crystals. If I only had the first one, I'd have that. That's what we just wrote down at the beginning of the class. If I just had the second one, I'd have that. But if I set it up such that it is indistinguishable which process happened, and there's no information I can determine which crystal it happened in, then those two different processes happen in superposition. And that state is this state tensored H plus e to the I alpha VV. That state is hyperentangled. Yeah?
I'm having a problem understanding the tensor product between the energy time entanglement and the momentum entanglement. Because don't I learn what the frequency is by measuring the momentum?
there are, let's see. So the question is, how does what you say makes sense? I'm thinking about that.
If it's just the transverse component of the momentum, doesn't that leave the along the original axis component?
It does. I mean, we're separating out. The question is, it's a little bit kludgy how I've done it. Obviously, we have from the phase matching condition over here, we have conditions on the longitudinal component and the transverse component, right? Now, it's all constrained, as you say, such that photons, right, okay, so that's the point. If I know that there's a whole continuum of directions, all of which that have the same color. So just writing the color doesn't tell me everything about the momentum. It tells me it's on its cone. What is really uncertain is the angle. And so that notation I've written isn't quite correct. It's not really about the transverse direction. It's really about the angular direction. And so there's really probably a better way to write this. I'll think about that for next time. Yeah, that you're correct. Okay. So I meant to bring my laptop because it was funny. I noticed something I wanted to show you on the screen, but I'll just show it to you here if I can do it. Let me just try that. So on the cover of, this is the current issue of Physical Review A. I'll just pass this around. And you'll see in the right-hand side there, the paper that's called Hyperentangled Photons. People are working on this stuff to this day. So this is quite au courant, as we say. Those of you who are studying French will remember this. And it's a kind of problem that to this day people are working on. How do you maximize, how do you optimize the situation in order to achieve this kind of hyperentanglement between polarization degrees of freedom as well as either color or transverse directions.
Are they actually doing it like this?
No, that what that paper is really about, I just glanced at it, is about integrated optics. So on a chip, how do you engineer dielectrics on a surface in such a way that it has all the right phase matching conditions in order to achieve this kind of hyperentanglement photons. All right. So we've talked now about this kind of entanglement between the photons, either in their polarization and or in their momenta or color. But what about mode entanglement? Let's see. Back from you, so get back to my notes. All right. So let's consider again when we first introduced the parametric amplifier. We did that in the context of squeezing, right? So the mode entanglement is related to the continuous variables. And when we talked about the quantum manipulation of the continuous variables, like the quadratures, well, what we did at the beginning of the semester is talk about squeezing. And it was that very same crystal, that very same process that led to squeezing. So there's something going on with the entanglement of the modes that we haven't yet considered. I mean, when I wrote down, and remember that the parametric, the II crystal, the Hamiltonian that we were working with was of the form, is chi2 is some, integral over all the possible down-converted pairs with a chi2, the pump amplitude, some function that's the phase matching condition of these guys, and then creation operators for the modes with the particular polarizations of interest, plus the conjugate. Right? This was the process that led to spontaneous parametric conversion. We annihilate the pump, which in the non-depleted pump limit were replaced by the amplitude of the pump, and then we created pairs or annihilated them. And remember, this is the generator of squeezing. Right? That is to say, if we looked at the case where we looked at the degenerate optical parametric oscillator or amplifier, then the unitary evolution was a squeezing operator that we studied at the beginning of the semester, which looked like this. So these are the creation annihilation operators associated with the particular mode, not degenerator, but degenerate. So this is some mode. Let's say that this is in a cavity, so let's call it an OPO. So we pick out one particular mode, which is degenerate, okay, with two green photons. So this is what's, now of course, when this acts on the vacuum, what we get is the vacuum plus R over the square root of 2 photons in that particular mode plus dot, 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 right? And what I have been talking about for the last half an hour or so today, and in my previous lecture, was just this term where we had a whole bunch of different creation annihilation operators, right? And so we had pairs of photons that were distributed differently, either in different polarization or different momentum. So I've been picking off this term. But in reality, we have this superposition of the vacuum with, say, 2 photons and 4 photons and 6 photons, and that led us to squeezing. So something is going on here in terms of the quadratures that is related to entanglement. So let's talk about that. Let me just first remind you to get a little bit of the formalism. Let's look at this in a little bit more detail. So, this operator can be decomposed into using the kind of form of the Baker-Campbell-Hausdorff theorem in terms that only involve exponentials of a dagger squared, a squares, or products of a and a dagger. So there is a way of decomposing that, which is the following. This is known as the disentangling theorem, and we get the following. This was in a, anyway, it's in, you can read about it. I have the notes to the original paper for that in the notes. This follows from the theory of Lie algebras on the group SU11, if you care. Okay? All right, so why did I bother doing that? Because now what I want to do is I want to act this squeezing operator on the vacuum for this one mode. What do we get? Well, when this acts on the vacuum, the annihilation operator is 0. So the e to the 0 is 1. The number operator is 0 on that. And so this becomes the square root of this thing, which is 1 over. So this becomes, when I look at this, this is equal to, writing it out in more detail, n equals 0 to infinity. 1 over the square root of the hyperbolic cosine of the squeezing parameter times this, acting on the vacuum, which is n factorial tanh r over 2 to the n a dagger squared to the 2n acting on the vacuum. Right? Just expanding that exponential. You buy it? So we see we get sums of pairs of photons here. This is equal to 1 over the square root of the cosh of r, sum over n, 1 over n factorial times, then we can multiply top and bottom here by the square root of 2n factorial. And I get square root of 2n factorial over n factorial 2 to the n tanh of r to the power n 2n. Okay, so this just is the exact expression which we never wrote down it before, I don't think. I was looking and I was saying, I can't believe I didn't write that for you guys before. But this is the exact decomposition of the squeezed vacuum. This is what we called earlier in the semester 0 with the squeezing parameter r in terms of the Fock basis. It's a superposition of Fock states weighted by these coefficients. Okay? And when r is small, it's approximately that. All right. So, what's the point? We're talking about entanglement. There's no entanglement here. This is one mode, and there's no different, we're not talking here about different momentum, different polarizations. However, as we said, this is the actual Hamiltonian, involves all the possible modes that are phase matched. So let's now look at the non-degenerate. Okay? The no-pogo. Where we have two modes. Okay? So we have a cavity that is doubly resonant. and it picks out mode A and mode B. They could be two different colors, okay, or two different polarizations. Typically, two different polarizations. Now, in that case, we studied that, I think, in homework, right? We had the two-mode squeezing operator. Remember that homework problem? And the squeezing operator in that case looks like this. So the squeezing operator, assuming I choose the phases just right, okay, where A and B are the annihilation operators or creation operators for the two modes. The mode associated with, I'm calling A, capital A, and the mode I'm calling capital B. And you can do this same thing in that case. And what you find is that the factors of 2 go away. This becomes a B dagger. This becomes this. You have the sum of the 2 plus 1. And the factor of 2 goes away here and here. Okay? So that's the disentangling theorem for the two-mode squeezing operator. All right? So now let us consider the action of this two-mode squeezing operator on the vacuum. This is what's called a two-mode squeezed vacuum. And that state is, I'll just call 0, 0, R, just like we had 0, R for the single. R is the squeezing parameter. Okay, let's do that. What do we get? Well, once again, this guy, this is annihilation operator, this is 0, e to the 0 is 1. This guy is 0, and then I have 1 over the cosh of R. And then I have this. So it looks like this is equal to right? These come from the Taylor expansion of the exponential. And factorials, I just divided them into 2 square roots. And then I have this. And so it has a very nice form. What happens to the cosh? It's out there. 1 over cosh R.
Why is it 1 over cosh R?
Huh?
Why is it 1 over cosh R?
Because I have e to the minus the log of that. Right. It's a funky way of writing. E to the log is the exponent, and then it's 1 over that because it's e to the minus that. Right? Okay, so but look, this is a key point. This two-mode squeeze state is this. This is mode entangled. The two modes are entangled. In fact, what we see here, without even trying, well, maybe trying a little bit, but not trying to do what we ended up doing, we got the Schmidt decomposition. This is the Schmidt decomposition of this entangled state. What are the Schmidt vectors? The Fock states. And the Schmidt numbers are here, or the Schmidt coefficients. By the way, this kind of state is often known as twin beams because the two, it's entangled such that if I were to measure the number of photons in one of these modes and I get n, well then mode B is its twin. It has also exactly n photons. So there is a correlation between the number of photons in these two modes. And that's sometimes called number squeezing because anything that's below is the usual. I mean, in a typical uncorrelated beam, you have Poisson statistics. So you're going to have Poisson fluctuations in the number of photons in the difference between any two uncorrelated classical fields. Whereas here, there's no difference. You squeeze that fluctuation in numbers, and that's called number squeezing. Okay, but wait, there's still more. Because there's a lot we can say about this. Let me just say a few of them now. Continue it next time. Well, since we have the Schmidt decomposition, we can ask about the entanglement instantly. For example, what are the marginal states? That is to say, the reduced density. Remember, if I have an overall pure state for the joint system, in this case the system is two modes, two harmonic oscillators, and I want, and this is their joint state. This is my state 0, 0, R. And I want to know how entangled are these two modes. Well, one way to look at that is to look at the entropy of the marginals, right? Because if they're not entangled and it's a pure state, then each marginal has 0 entropy. And if they're entangled, then when you trace over that, you lose information in the correlation, so therefore there is higher entropy in the marginals. So what are those marginal states? For A and B? Well, they're diagonal in the number basis, right? So what I have here is the sum n equals 0 to infinity, some probability distribution, and for either mode or A or B. It's the same state, right, for the marginals. What is Pn? Right, it's the square of the Schmidt coefficients, right? So Pn is equal to tanh R to the 2n over cosh R to the n, right?
Just squares. Just squares.
Oh, to the squares. Yes, thank you. The reason I was thinking about that, of course, tanh is sinh over cosh. So this is sinh of R squared to the power n divided by cosh r squared to the n plus 1. Now, you might remember some funky thing about something to the n over something over to the n plus 1. It's a thermal, something about the thermal state of bosons had that. In fact, cosh squared is 1 plus sinh squared. It's one of those funky hyperbolic identities. So this is equal to sinh squared to the n over 1 plus sinh squared to the n plus 1. So voila, we know that this, the state, the marginal state, if I have a two-mode squeeze state, which is a pure state, and if I look at the marginals, they have entropy. And that entropy is exactly the entropy of a thermal distribution, with the mean number given by sinh squared. If you were to take this probability distribution and ask what is the average number of photons in that mode, it would be sinh squared. So this is a beautiful result, it's an important result. A two-mode squeeze state is a thermal, is a pure state, but the marginal states are thermal. With the mean photon number that has to do with how much squeezing there was. Squeezing. So now I ask you, what is the entropy of these marginal states, and thus the entanglement of these guys? How would you find it? Well, maybe that will be one for homework, but I'll give you the answer. The entropy is equal to, which is the entanglement, so this is the entropy of the marginals. So that's equal to minus Tn log Tn. Pick your favorite base for your log, calculate your entropy. Well, why don't we just do it? Because I don't think we have any room for homework. Just do it. Plug in this for Pn. So I'm going to do it. The log of this is n times the log of average n minus n plus 1 log of average n plus 1. Right? All right, so that is equal to summing n with the piece of n is, it's, again, the average n. So this is equal to minus average n log of average n plus average n plus 1 log of average n plus 1. Which, if I chose to, I could write in terms of this as minus sinh squared r log of sinh squared r plus cosh squared r log of cosh squared r. Somewhere sign is wrong. I don't know where. Maybe it's right. Okay, so that's an interesting fact. We have mode entanglement in a two-mode squeeze state, and that mode entanglement is related to the notion that each individual mode looks thermal. Now, I guess, given the time, I'm going to stop there, but there's still more to think about. And that I wanted to talk about, I'll just give a prelude to that with the following statement. What about the quadratures? Well, for a single mode squeeze state, we had the following. The squeezing unitary rescaled x and p. Right? Such that I maintain the commutators, but I scale this down and scale this up in the inverse way. What about the two mode? Well, the two mode does the following. If I look at the sum of the quadratures associated with mode A and mode B, which one is which? Is the sum or the difference the way I've written it? Yeah, that's the difference, right? And the conjugate is the sum of the momentum. They commute. This one is a minus as well. And then if I look at the plus, that would be plus, and this is the minus. So, what the two-mode squeezing operation does to the quadratures is to correlate them, and thus entangle them. Suppose that the squeezing was very large, so that this was approaching 0. Well, that would say that the difference between XA and XB approaches 0, so that XA and XB are highly correlated. If I know XA, I definitely know XB. And what it also does is correlates the momenta, such that if, as the squeezing approaches infinity, as R goes to infinity, P gets correlated in for mode A, becomes correlated with minus P for mode B. Does that sound familiar? It might, if you've ever studied the Einstein, Podolsky, and Rosen paradox. So in EPR, what EPR considered was the situation that was exactly the case where this was infinite squeezing, whereby you had an entangled state such that if you knew the position of one particle, you can automatically predict the position of the other particle because they're entangled. Simultaneously, if you knew the momentum of one particle, then you automatically knew the momentum of the other particle because they're anti-correlated. So the state that comes out of the non-degenerate parametric oscillator, the two-mode squeeze state, this state, the twin beams, is an approximation to the EPR state. It's only exactly the EPR state when R goes to infinity, but it's an approximation to that state. And thus, what we're going to study next time, we'll review for those who've seen it, and we'll go into it for those who haven't, is the whole EPR paradox, Bell's inequalities, and how tests of Bell's inequalities have been carried out in quantum optics. That's where we're heading. And we'll conclude our study of entanglement with that. All right?